Good afternoon. It's my pleasure to introduce you to Professor George Dulikravich from the Department of Mechanical Engineering at Florida International University. For those who don't know him already, Professor Dulikravich has been here in Coppe working with us for a couple of times. I'm going to share with you some of his major professional accomplishments, which are many actually. So, and in fact, we have a great honor of having his lecture exactly today, because he has just mentioned to me that 40 years ago he has received, exactly 40 years ago he has received his engineering degree in aeronautical engineering degree in Belgrade. Professor Dulikravich has authored and co-authored over 400 technical publications in diverse fields involving computational analytical fluid mechanics, subsonic, transonic, and hypersonic aerodynamics, theoretical and computational electromagneto-hydrodynamics, conjugate heat transfer including solidification, hybrid optimization algorithms, computational cryobiology, acceleration of iterative algorithms, computational grid generation, multidisciplinary aerothermal structural inverse problems, design and constraint and optimization turbomachinery, fluid flow and heat transfer in networks of micropassages, and multi-objective optimization of chemical compositions of alloys. Actually, his vast experience in many fields in engineering, from this perspective, we kindly invited him that during his visit. He's actually here in a project, Science Without Borders project, that is coordinated by myself and Professor Marcelo Colasso. Instead of having him here only working with us, that we do this all the time, we kindly invited him to share his experience with us this afternoon. And the timing was very suitable because we have these 50 years of Coppe this year, so the timing was very suitable. Professor Dulikravich is also the founder and the editor-in-chief of an international journal. It's called Inverse Problems in Science in Engineering. And he's also an associate editor of 9 additional journals. He was the founder, and he started 2 conference series. One of them was called Inverse Design Concepts and Optimization in Engineering Science. And this was in the late 80s, early 90s, right, Professor Dulikravich? And when not many people talked about inverse problems, and I mean that actually most of the people even didn't know what it meant, he was one of the first to start working on this area and actually promoting this interesting approach for engineering problems. And he also started the International Symposium on Inverse Problems in Design and Optimization. It's the IPDO Symposium, which we had the first one organized here in Rio de Janeiro in 2004. And we are now going for the 4th one this June in Albi in France. Currently, he's the head of the multidisciplinary analysis, inverse design, robust optimization and control laboratory at which he personally founded in Florida International University. Okay. So besides this talk within the scope of the 50 years of Coppe, he's also going to give some more specific lectures this week and also early next week. So on Thursday at 1 p.m., Professor Dulikravich is going to speak about materials by design, direct and inverse methods using multi-objective evolutionary optimization. On Friday, the title of the talk is Electromagneto-Fluid Mechanics, Mathematical Models and Numerical Simulations. And this coming Monday, the title of the talk is Optimization of Cooling Protocols for Human Organs. So very diverse lectures, which actually demonstrate his large experience in interdisciplinary and also multidisciplinary problems. Okay. So these other talks will be all held in the Laboratory of Heat Engines. It's at 1 p.m. Okay, so this coming Thursday, Friday, and Monday. Okay, so Professor Dulikravich, please have the floor, and let's give a hearty welcome to Professor Dulikravich.
Good afternoon. Thank you very much, Professor Orlando. Thank you very much for coming and taking time from your research, your work, to listen to my speech. Before I start, I just want to clarify one thing. The sequence of international symposia on inverse problems, design, optimization was co-founded with Professor Orlando in 2004. And the first one was held in Rio, second one in Miami Beach, third one in João Pessoa, and the fourth one will be held next month in Albi in France. So, since you've heard just about everything about me, I guess I think nothing more to tell you. I really wondered how to structure this entire presentation. The title is a little bit suspicious, almost like I have some crystal ball I'm going to looking at and predicting the future. I will try not to do that. I will try to substantiate at least some of the main things that I'm going to talk about. So quickly, I'm currently at my fourth university in my career, teaching at Florida International University. This building here is the College of Engineering, which is about 1 kilometer away from the main campus of Florida International University. And university is about 15 minutes from Miami Airport. Okay. So it is the largest Hispanic producing institution in the country, especially in engineering. We get the largest number of engineering degrees than any other university in the US. The entire university currently has about 48,000 students. Okay. At least 2/3 of all the students speak Spanish and English. I mean, they can switch in the middle of a sentence, switching from one language to another, totally bilingual. Okay. Students are from all over the world. The students from about 125 countries. Okay, you heard about me, I guess, what I've been doing. Let's start with some of the business. So to give some credibility to this lecture, I also listed down where I got some of these data. This is sources from World Bank. And this was a few years ago, but it still pretty much holds. So here we can see different aspects of activity of research in different countries in the world. Notice that Brazil is this reddish color. So Brazil is about here. The optimum would be, of course, the thin black line around. Okay? So if you look where Brazil is lacking compared to, say, China, India, Japan, Russian Federation, Singapore, it is this area here. And this says researchers in research and development per million people of population. So number of researchers in Brazil per each million of population is much lower than it should be. Therefore, universities in Brazil should produce more researchers. Okay? In other words, these people should not just quit after bachelor's degree, they should continue to graduate school, get a master's, hopefully their PhD degrees, and get into research. Okay? In other activities, Brazil is doing quite well for the time being. Of course, it is rapidly improving. So let's see how much money are different countries spending on research. United States is spending about 31% of all the money. Here we're talking about 3 years in a row, okay? And this is from Battelle Research Institute. All the rest of the North America and South America together spends barely a little bit more than US. Asia, the entire Asia is also roughly in the same level. Japan alone, China alone, India, etc. Okay? Europe is definitely lagging behind. Suspiciously, Europe is lagging behind in total number of dollars, if you wish. Okay? Now, the global research and development spending forecast for this was done in 2009. You can see basically how it is projected that U.S. spending is going to stay relatively flat, which is true. However, in Asia, look at this, 1.8% to 1.9%, okay, increasing. In Japan, they strictly, their survival depends on new advanced products. So they're investing much higher percentage of their gross domestic product into the research and development. China is also increasing its percentage, although the gross national product is also increasing tremendously, okay? India is relatively flat. Europe, pretty flat, okay? And then the rest of the world, of course, limps around. So let's try to see on the map here, a very interesting map, and this was basically in year 2011, just 2 years ago. On this here, we have research and development as a percentage of gross domestic product. That's what we saw a moment ago in this table, okay, on this axis. So this is a percentage of gross domestic product, and here is a number of scientists and engineers per each million people. Well, let's look who is the worst and who is the best. Those that spend least amount of money and has the least number of researchers are basically in this corner here. Those that are spending the largest amount of money, okay, and have largest number of people in research are here and here. US is basically here. European countries are pretty much in this region here. And then comes China and Brazil. So obviously the trend is from here in this direction. So Brazil is obviously moving in this direction. Hopefully increasing the percentage of national gross product devoted to research and development, and hopefully increasing the number of scientists and engineers working in research. Here's another forecast, gross expenditures. Similar, United States is spending tremendous amount of money, obviously, on research. China is, well, this was prediction 3 years ago. China is doing, obviously, rapidly increasing amount of money on research. These are talking about billions of dollars. Japan, similarly. Germany, kind of, staying flat. South Korea, doing, I don't know, strange kind of motion, but basically relatively flat. Okay, France. So usually Europe is not really moving forward with the amount of money spent on research. Now let's look at Brazil. 1.1%, 1.2, 1.25. So very mild increase in gross national product devoted to research. And of course, the rest of them are listed here. This is ranked in the number of dollars, billions of dollars spent, okay, for the whole world. Now let's look at the ways research performed. It's performed in the industry, which is blue here. It is performed in government research laboratories, which is this yellow color. And it is performed in academia, universities, university research centers, like this one. This is very, very interesting slide. This shows how much money was spent in industry on research, in government research laboratories, and in academia. And this shows how much did they perform. Okay? What did they produce with this money? So industry produced, basically, at least this is for the United States, produced a little bit more than was invested. Government research labs performed pitifully. They produced barely $29 billion worth of product, and they consumed $126 billion worth of product. So this points at the incredible inefficiency of government research laboratories. At the same time, if you look at university research cost about $31 billion, but produced 61, double that much. So governments should invest, from this simple logic and this simple data, should invest much more money into university research and much less money into government research laboratories. Okay. Here's another interesting plot, again, Battelle Research Institute. It shows basically which kind of industries are most profitable, or which industries are spending most money on research. Where is the value added highest? In what kind of industry? Okay. And here we can see that research and development spending per number of employees. Okay. So per each employee, how much money they're spending. This is in this direction. And here's research and development spending as a percentage of the overall sales, net sales. Look at this. The main performers are what? Look at the names of these companies. Merck, Roche, Lilly, Bristol Myers Squibb. These are all pharmaceutical companies. So pharmaceutical companies and pharmaceutical products obviously are the highest, the most profitable industries. Okay? Profits are the highest. Okay? Because they're obviously investing largest amount of money also to achieve it. Oracle, all of these electronics industry is basically in this blob here. Okay? And then you go down to car manufacturers. Some of the, I think Boeing should be somewhere also there. But mainly car manufacturers. In other words, very little is invested in car industry research, and large corporations that produce general machinery. And obviously this indicates that the profit margin in these industries is very slim. Okay? Please remember this slide. We'll sort of, on the basis of this, look at some of the analysis now. So let's look at these industries that spend most of the money on research. In pharmaceuticals, this is the list of the main companies. Okay? And you can see basically how they are ranked as far as what percentage of their gross net product actually they're spending on research. The profitability of new medications and so on is incredible, obviously. So what are they doing? They're doing just medications, pills? Not really. Look, most of the money they're spending on stem cell applications. So research on human stem cells, rejuvenation of our organs, repair of our organs, okay, and curing certain pretty nasty diseases. Right next to it is detection and monitoring of human body. So all sorts of nuclear magnetic resonance imaging, all sorts of imaging systems, all sorts of sensors, implantable or external, okay, or in our shoes or in our fabric or clothing and so on, okay. Genetically modified agriculture, very interesting. Pharmaceutical corporations are also making money in genetically modified agriculture, plants, okay. Biomarkers, sure, to detect certain diseases, to track them down and so on. Surgical implants, these are more of the classical applications. And eventually, pharmaceutical products. All sorts of pills, drugs, and of course, creams, etc. Now let's look at the electronics industry. Who are the leaders? Okay, Apple, Google, etc. These are spending most money on research, okay? And then down the pile. What kind of research are they funding? Predominantly wireless communication. So most money in electronics companies is going on wireless communication. Okay? This is the key to all of the new devices. Of course, embedded technologies, energy harvesting system, this almost didn't exist here just a few years ago. It very rapidly grew to something very noticeable. basically how to pick energy which is totally negligible, so to speak, and convert it into basically electric energy in order to make some of these electronic systems actually work. Of course, sensors, the detectors, this is standard. Energy generating systems, fine. Bioelectronics, interesting. Lots of implantable chips and so on will have to actually take energy from our tissues in our body. There'll be no batteries to be in, no batteries from the outside. They'll be feeding on energy, chemical energy from our cells, okay, to keep on performing detection and to send the signals out wirelessly. Remote sensing networks, networking, solid-state lighting, so on. But main thing is here. That's what's fundable, okay? In aerospace industry, of course, big boys, Boeing, Lockheed Martin, etc., okay? What are they funding? Airplanes? Not really. They're actually spending lots of money on robotics and drones. Drones means vehicles without pilots. All the Air Force is going into pilotless Air Force. They already announced a week ago that they successfully launched a jet-propelled airplane from the deck over of a Navy aircraft carrier. And by this August, they're also going to have this airplane land on the deck of a aircraft carrier. Not radio controlled. No, no, no. Strictly acting based on its sensors, of course, lots of radar systems, and artificial intelligence embedded in its own software, in its own hardware. So all sorts of unmanned aerial vehicles, unmanned underwater sea vehicles. There's a tremendous interest in this area, and obviously that's what's reflected here. Cybersecurity, very interesting. If you looked at this just 5 months ago, 5 months ago, cybersecurity was probably there. Right now, cybersecurity is probably here. Since Happy New Year, cybersecurity jumped, I'm sure, way ahead of anything else. What's the point? Well, the point is that industrial espionage is a new form of warfare, which is very soft, of course. And this means acquiring knowledge from certain data banks, from certain computers, from certain communications, and so on. Okay? How can we protect all of these so that nobody can intrude and steal our whatever knowledge, secrets, etc. Okay? Obviously, industry is interested in this as well, not just military, because industry doesn't want to lose this precious information they have, which is proprietary, to somebody who didn't invest any money in this. Okay? So cybersecurity became extremely important. Right now, it's number one in importance in all government agencies in the United States. Autonomous vehicles, basically same thing as drones, and of course, the rest of it goes down the line, quite typical. Laser-based weapons. Well, we'll come back to this briefly. Laser-based weapons, basically all sorts of lasers, ion beams, electron beams, directed energy beams. Every NATO soldier was supposed to have, by year 2025, a laser gun. Not to point out, what he's talking about, but to shoot and blind permanently the other soldier. Okay? So here we're talking today about energy beams which can shoot down an airplane about 150 kilometers away. Not any further because of the curvature of the Earth, right? Problem. We'll also briefly talk about how to defend from this. And of course, stealth technology. All sorts of materials, coatings, etc. Metamaterials that are going to make, hopefully, objects invisible. They're going to bend the electromagnetic waves in such a way, so light waves, that basically we cannot see the object. Okay? All militaries in the world are frantically working in this area. Okay? This area is not going to go away. This will be around for years to come, really well funded. So let's look at the energy sector. In the energy sector, of course, we have big boys doing all sorts of energy generation using steam turbines, huge industrial gas turbines, and of course the guys that are extracting petroleum from the earth and the natural gas, etc. But you can see here that energy, global generation is going up, and also US generation is going up. Not anything dramatic, okay? But obviously there's a growing need. So what do people invest in research? What in energy area? What areas? What specific topics? Well, it turns out, at least 3 years ago, that they predicted that by 2014, fuel cells are going to be consuming most of the money for research. I'm afraid that this is not true anymore. Okay, hybrid systems, yes, for cars. Okay, biofuels, surprisingly, this is really growing faster than expected. Photovoltaics, it is very strong. It will maintain there. Chemical batteries, this has definitely moved forward. There's tremendous need for storing electrical energy in a compact batteries and being able to withdraw this energy in a very short period of time, discharge it, and also charge these batteries again in a very short period of time. And do it many, many times, of course, without damaging the battery. So, quite a challenge, and the number of people and companies are working in this area. Natural gas, with the fracking, this has exploded completely, but there's not that much investment in research there, because methodology or technology has been developed, and now it is basically exploitation. Wind turbines, sure, people design all sorts of aerodynamic superior blades, etc. So here the main research is in making the mechanism, transmission mechanism, and generators more efficient. Okay? And of course, control system more efficient. And then the rest of it, hydrogen energy, clean coal. Clean coal, interesting, is also very, very popular. If one can drive price of liquid, which is basically gasoline obtained from coal, to be more than to be less than $30 per gallon. If it is less than $30 per gallon, well, up to $30 per gallon, then it is directly competitive with the gasoline obtained from the petroleum, from the earth. Because above $30 per gallon, everything is profit for the companies. So what we are paying right now, just look at the price of gasoline, and price of barrel of oil, basically, it's close to about $100 per barrel, anywhere between 80 and 100. So from this you can get some feeling how much money a petroleum company is making. I guess you all are familiar with this. You have Petrobras here, and Petrobras has lots of money to give to universities and everybody else. So anything that costs them more than $30 per is pure profit. Okay? It's only how they well manage this profit or squander this profit, that's a different story. Okay? But clean coal is also a big area, especially for the countries that have cheap coal, low grade, low quality coal. Okay? Ocean power, geothermal, blah, blah, blah. This is all relatively much smaller investments in this area. And of course, internal combustion engines, there's still some research improving efficiency, etc., diesel energy, etc. But these are incomparably smaller than research in these areas indicated above. In chemical industry, of course, the big boys, Dow Chemical, DuPont, 3M, and so on. These are huge companies, corporations. And we can see also global investments in research going up worldwide, and also in this country. What are they invested in? Nanomaterials. So big boys in chemical industry are investing a lot of money, most money, in application of nanomaterials. All sorts of composites, photovoltaics, yes. This is definitely booming, okay? Biomaterials, absolutely, okay? Thin films, coatings, lots of money spent there. Energy efficient processes and so on, okay? So classical, of course, was plastics, polymers, ceramics. This is sort of a classic area. But real money is being invested in these areas. World's 2,500 largest public corporations by region. Where are they located in the world? Okay. In US and Canada, well, look at this. In 2000, there were 1,050 of them. In 2010, it dropped down. In one decade, the number of the largest corporations in the world dropped down to 750 in US and Canada. Okay? Let's look at China. Nothing, 250. Okay? So China is starting to have huge, huge corporations. Brazil, Russia, and India were relatively flat. They're increasing also. Okay? Japan, relatively flat, but also starting to drop down. Western Europe also dropping down. So obviously it is Asia, specifically China, that is having dramatic increase in the number of these corporations. And the question is, where are American companies, corporations, investing worldwide in research and development? On Ilha de Fundão, you have a bunch of research centers built by international corporations. The question is, why are they investing here? Okay. Well, U.S. companies are investing in research in China. Of course, in research in America. Oh my God, these are U.S. companies. Okay? Where are U.S. firms planning to expand their research and operations? More in China than in North America. This is shocking, right? We're not talking about production facilities. We're talking about research centers. Okay? So, expect to see more of these research centers being built in Brazil in the near future. This is good news for you. Good news for your students, okay? For all the Brazilians. And of course, the rest of them here. So the question is really, where should we, what kind of industries are the best value-added industries? Where is profit margin the highest, okay? Well, if it is textile, shoes, and this kind of toys, this is what China used to do 20, 30 years ago, okay? China evolved into this. China is now doing cars, doing electronics, okay? China is doing the all sorts of household goods. These are the highest profit margin industries. And this is what Brazil is also starting to experience, okay? Textile industry is starting to die in this country, okay? Leather industry, shoe industry, they're starting to go down because they require too much of a unskilled human labor, okay? And the profit margin is very low. So briefly, if I can be brief, this is a very challenging thing. I will try to run through some of these topics. In healthcare, obviously biomaterials and tissue engineering are, as we have learned already, are very interesting areas where the research is being funded. Biotechnology, pharmaceutical biotechnology, of course. And of course, as you can see from this brief write-up, there is quite an explosion in the field of medical technology, building new methodologies for transplanting organs, for implanting different sensors, artificial, whatever, joints, parts of our muscles, cardiovascular system, etc. Okay? Here's an example of a person who was actual living person, who was a convict, because he killed somebody. They then executed him and froze his body. They sliced his body at 1 millimeter slices. And after each slice, they took a nice photograph with a digital camera. So they characterized 42 different types of tissue in the human body. And for each of these tissues, they separately measured specific heat, thermal conductivity, whatever else, okay, physical properties. And then, of course, from this database, we can always reconstruct the entire human body using simple voxel technology. Here we just looked at the situation of reconstructing the head of the human head with all the real contents of this head inside. So each of these finite element grid cells had its own physical property assigned to it. And then the idea was, let's try to simulate, if it is possible, to cool the brain in the case of a stroked patient. Because if a person has a stroke, this means the blood vessel burst in the brain, and this blood, which spilled, is building a pressure very quickly. And this part of the brain does not have new oxygen. Brain tissue dies fastest of all the other tissues in our body. So if brain tissue dies, and this part of the brain happens to be one that controls my speech, I will not be able to give you any more lectures. One good outcome, right? Or it can control locomotion. I can become permanently paralyzed in a part of my body. If I can somehow cool this brain as fast as possible, I can slow down the decay, the chemical decay, the metabolism. Fancy word is metabolism, rotting of the brain. Okay? Just because you want to have your steak, when you go to the store, you buy a fresh steak, bring it home, if you put it in the fridge, it can stay there for a few days, right? If you didn't put it in the fridge, if you left it outside on a table, and went out to a movie or something, come home, it's going to stink, right? Well, it's exactly the same concept here, no science fiction, right? So obviously, somebody came up with the idea, if we have just like a scuba diving gear, double wall rubber cap and suit, and we pump very cold fluid through this double wall, that can suck off the heat from our head and cool the brain. It's pretty naive concept, because this person didn't know much about physiology or heat transfer to start with. Okay? Our brain has a skull, which is ceramic porous material, which is extreme thermal barrier, and then brain is permeated with the microvessels. So it's cooled in a superb fashion. I mean, warmed in a superb fashion. Okay? So whatever we remove this way is going to be replenished very quickly with the fresh blood. So, company wanted us to simulate if this is possible to cool the brain within first 60 minutes. Why 60 minutes? Well, if the person is discovered and transported across Rio to hospital and put on an emergency table so they can drill a hole in his skull and relieve the pressure, within 60 minutes, this person has reasonable chances of recovering the physical functionality, whatever was happening. Well, if it is more than 60 minutes, this person is going to be vegetable, okay, or will die. So, just three-dimensional unsteady finite element, spectral finite element simulation reveals here that if we shoot, if the blood is already a little bit pre-cooled at about 35, oh boy, guys, acting in, huh? Oh yeah. After 1 hour, sorry, but this brain is still perfectly warm. Actually, it took 2.5 hours to cool the brain with just a cold cap. Okay? So this is another way to do it. But if we jab a needle here in one of the main blood vessels and divert the blood through a small heat exchanger, which already exists on the market, then in 4 seconds, this blood is pre-cooled and we're shooting into this carotid artery into the brain. 4 seconds from here into the brain. So if we do it in such a way that we pre-cool the blood to 35 degrees centigrades, okay, then our simulation shows no problem. Actually, in about 30 minutes, we already are dropping down to about 29 degrees centigrades. Okay? So this is power of computational simulation versus intuition and brute force that works perfectly well, at least in Australia, where Professor Barnard at the University of Melbourne has saved several hundred human lives by doing exactly this, okay? Without any simulation. So basically, he just, in a very straightforward manner, they would grab the patient, throw him on a helicopter, and fly him off to the city emergency hospital. And while on the helicopter, they would jab him with the needle here, and then connect this with plastic tube to the plastic sack with the crushed ice and water. And ask him then what did you do? Well, then we squeeze this. Okay, we squeeze this. Which means the cold water goes in and mixes directly with the blood. So you get pre-cooled blood and water mixture, which in 4 seconds is shooting inside the brain. That's how they practically achieve their 31 centigrades. Okay? In America, this is not allowed. This is against the law. So people have to die because of the lawyers' rules. We are not allowed to do that. So just to point out how certain very simple procedures could be simulated by us engineers, okay, and give tools to people to design new things that can save human lives. Okay. Of course, here's just another one. Pre-cooled 35 centigrades is pre-cooled to 31 centigrades. Cools perfectly well, right? Designing new materials. Design and optimization in chemistry, in chemical engineering, is a wide open field. Offers incredible opportunities. This is just example of master degree, one student who did it with me about 2 years ago, designing new type of refrigerant. So refrigerants are things which are in your car, in your refrigerator, in the air conditioning system in the building, and so on. So we want to design new refrigerant that's going to have extremely high latent heat to phase change and all sorts of good things that we would like to have. So using optimization, multi-objective optimization algorithm that we had, he came up with this structure of the molecule. Moreover, exactly the same equation that he came up with gave him this topology. But it turns out it's just one of the 4 isomers. Each of these satisfies this equation, but only one of them provides these desired properties. So now think about, not about refrigerants, think about medicines. So this open field of designing medicines for me, for you, okay? For my body, for my illnesses, for my strengths, for my age, okay? Rather than doctor prescribing, oh yeah, 20 pills of this, okay? Which means half of this is going to be poisoning my body, and hopefully the other half may be helping cure whatever problem I have. So design and optimization in chemistry, in chemical engineering, of course, this is directly applicable in all sorts of fuels designs, energetic materials, adhesives, detergents, name it, okay? Rebuilding ourselves. There's tremendous effort in this area. Every single company in US is doing research frantically in this area. Basically, think of this. So I've been drinking a lot, and my liver is completely, giving up. Well, I have to wait for somebody to die whose liver is going to be compatible with my body, so they can take this liver, hopefully I can live somewhere close to this place, and be high on the waiting list, so they can transplant liver into my body, and then feed me for the rest of my life all sorts of crazy medications, just so I do not reject this transplant liver. Okay? Versus, if they take this liver out, and I'm going to explain it in a very kindergarten language, and they soak it in special kind of liquids. These liquids are going to eat up all the tissue of the liver and leave just a spongy kind of scaffolding. Okay? So you have a leftover of the liver is going to be looking like a sponge. Now take this sponge and put it in another pot. And this pot has very special chicken soup inside. Okay? This chicken soup is made of my own stem cells from my body. And with the proper flow of this chicken soup with my stem cells, these stem cells are going to start attaching to this spongy material, this scaffolding, and regrowing this liver. This is not of science fiction. This already works. Okay? But it's still in the stage of laboratory experiments because it takes several years to be approved by government agencies, etc. Okay? So this is an area where classical mechanical engineers in thermofluids, etc., could join hands and do a tremendous job with the people that are in biomedical engineering. Okay? I already talked about energy, cold to liquid conversion, and so on. Biomedical devices, of course, I talked about this a moment ago. Energy transportation. Well, that's very interesting. Today it's very politically correct to talk about something that is going to be alternative energy source. And we have, of course, something that is sustainable. It's not fossil fuel, not coal, not petroleum, not natural gas. So we're talking about wind energy, solar energy, sea, ocean wave energy, and of course ground energy in terms of industrial plants. Okay? So here's very interesting analysis of this. Solar energy, here's just an example of what a profitable solar farm looks like. Look at this. This is a huge expanse of a desert in Southern California and Northern Arizona. And these are all mirrors, okay? Solar mirrors. These are houses here. These are houses. Look at this. Look at the scale of this. And this is just one half of this. Here's the center, okay? So another one goes over here. Okay? So capital investment is something like this. The huge chunk of land required for this. And of course, good Lord is going to say, sun is going to shine, constantly, 365 days a year, and then you're going to be profitable. So, of course, to increase the chances of being really profitable, we have to also play with other things that come into this. And this means, for example, the fluid. Fluid has to be heated up, phase changed, and then, of course, this vapor is going to be high pressure, high temperature, driving whatever turbines, which are going to be eventually generating our electricity. Okay? So there is a big fight between the groups which are promoting alternative forms of energy and those that are basically saying, this is not reliable, this is not possible. Okay? So this energy analysis here says, let's look at how much land is required to produce a certain amount of energy. So let's say here, if you're having just concentrated solar power stations in a desert, for example, they can produce 15 or 20 watts per square meter on average, year-round, presumably. Okay. Now, for example, in Germany, you have Bavaria. Well, Germany doesn't have that much sun. Okay. So solar parks in Bavaria produce only about 5 watts, not 15 or 20, 5 watts per square meter of land area. They don't have deserts, that they use land area, right? At the same time, say hydroelectric facility, say Scotland, the power per surface area is about 11 watts per square meter of a lake, okay? Either man-made or natural. But look at this one, wind farms. If they are in windy locations, so let's say good God says, and let the wind blow, and the wind blows day and night all the time, okay? Same speed, same profile, blows, okay? Produces roughly 2.5 watts, only 2.5 watts per square meter of land or sea on average, because the wind turbines in the ocean as well. The best energy crops in Europe, we're talking about corn, okay? They're going to be converted into alcohol. Deliver only what? 0.5 watt per square meter. So what is the logic of growing corn to produce energy as compared to wind farms and to solar farms? Okay? It's quite an issue. So let's look at the other possibility. If the world average is just need is 0.1 watt per square meter, let's say this is average for the whole world, okay? Then let's look at what these are going to mean in as far as what is the required surface area needed for it. Let's say if a country with the size of population of Britain, which has 61 million people, is adopted, according to this, then nearly 10% of the entire United Kingdom, okay, will have to be devoted to some sort of alternative energy sources. 10% of United Kingdom will have to be covered with the wind energy, whatever, solar farms and so on. Okay? If it is purely solar stations, okay, then this would be in case of crops. Sorry. If it is solar stations, then the area we have to cover just solar stations. In England, we have 5 times the entire London area. Okay? And of course, as a comparison, let's look at the extreme. It would require only 50 nuclear power plants to provide the entire United Kingdom with electricity. And this would take about 50 square kilometers. So as far as the efficiency of the use of the territory of a country to just produce energy is pretty mind-boggling here, right? Of course, nuclear mini reactors are totally new thing as far as design. They're not old high-pressure water-cooled nuclear reactors, but they're usually helium-cooled, so the amount of radiation in case of any leak and so on is absolutely minimal. They could be built in only 2 years, not 10 years. And they can provide power for smaller cities, okay, rather than huge chunks of country. But the main showstopper is, of course, general public fear of radiation, okay, especially after Japanese disaster with the tsunami. Internal combustion engines, we've already seen, are not getting that much money for research. Electric cars are waiting also for reliable, large capacity, compact, inexpensive batteries. So batteries in cars is the main showstopper. Okay? The main area that research should be focused on. In addition, for example, Toyota Prius, electric motor, currently uses about 30 kilograms of rare earths. 30 kilograms of something expensive and very hard to get. And but China can stop selling it anytime they wish. Okay? This is not good. Thin film compact batteries, electropolymer batteries, wireless energy transfer, eventually this is the way to go, obviously. Energy grid, electric grid, and wireless energy transmission. These areas have been heavily funded in US. Of course, grid in most of the countries is very fragile, very inefficient, and so on. And there are damages to it due to power surges, due to weather, solar storms, and so on. Tesla's idea from 120 years ago, from his experiments in Colorado, obviously is still something that 120 years ago we still do not know how to duplicate it. How to light the light bulb 25 miles away from the power station. Okay. So research is needed in these areas. Another large area, very acute for this city as well, for all the cities in the world, is trash. Human refuse. Here's a very interesting piece of news. So New York City, which decided not to implement the use of trash, is sending 10,000 tons of trash out of the city every day. New York City is shipping out on barges 10,000 tons every day. Well, if they do it for 40 years at $100 per ton, it's going to cost them $15 billion that will leave the city of New York. Quite a loss of money, right? It would be much better to invest building some of the factories that are industrial units that are using this trash and converting it into energy and some other usable products. I'll go over there. Do I have a few more minutes? So, okay, sorry. Water treatment and desalination and purification. There is at least in countries of third world, including China. I didn't even want to show you what China has. China has a horrendous problem with the water pollution. Go to China and tell me if you didn't get stomach problems to start with. But if you just go and see what the rivers and lakes look like, it is shocking. Okay? So cleaning these things basically, there's a tremendous need for compact sewage treatment plants for cities. Okay? And of course, they should use combination of electric fields, chemicals, and aeration. For water desalination plants, especially like Middle East and so on, same story. One should use new designs and use readily available energy, which is solar power, obviously. Drinking water is becoming rapidly an issue worldwide. The shortage of clean, safe drinking water. So design large capacity drinking water purification plants using combination of electric and magnetic fields for solid particulates removal, safe chemicals, and of course membrane filters, including electromembranes. So again, electrical, mechanical engineers would have quite a field doing this. Genetically altered vegetation, you're seeing some of the pharmaceutical companies actually pumping money in this area, right? Almost all industrial plants are already genetically engineered. All the vegetables, fruits are already genetically engineered. Go to store, and most of this already is not really natural, okay? But there's a need to re-engineer most of them by using, let's say, constrained multi-objective design optimization, so that such crops are minimally harmful to our health, okay? At the same time, giving maximum yield and using minimum amount of land and fertilizer. Very similar story for livestock. Almost all the livestock, including cattle, pigs, sheep, chicken, all of this is already heavily genetically altered, okay? However, again, this has to be re-engineered in order to get this kind of meat produced or protein produced, from animals that has a minimal amount of, that requires minimum amount of feed to these animals, so be most profitable, minimum amount of time to grow or mature these animals, and create minimally negative effects on human genetics by consuming these kind of animal products. Of course, if USA was able to implement heavy agriculture mechanization and irrigation system, like in California, more than 50, 70 years ago, Brazil should also be able to do the same. If Israel was able to do this in a desert, Brazil should be able to do the same. Okay? Brazil should become one of the major exporters of bulk food. It already is, but could be much more than it is. Okay? Now I'm talking about something where Brazil should be able to invest and produce better things. Defense. Well, one area which I mentioned earlier was directed energy weapons. Lasers, ion beams, electron beams, either steady or pulsing, with quickly changing frequencies and so on. An example, let's say we have just 1 million joules delivered as a laser pulse, ultra high heat flux, okay? Say 1 kilowatt per square centimeter. Nothing special about this, okay? This would be basically something equal to the 200 grams of high explosive going on at the surface of this object with this beam hits. Okay? Well, today we are already talking about, you can buy on the open market lasers which are of about 10 to 20 kilowatts, actually 20 kilowatts. You can already readily buy a laser, which is about this size, a small refrigerator. You can buy several of these with the proper optics. You can create a laser of 100 kilowatts easily. Now, 100 kilowatt laser beam can burn quite a hole in quite a few things, okay? And you can buy it on the open market. The primary damage mechanism, of course, is the surface not just heating, not just melting, but explosive evaporation of the surface, whatever the surface is. Okay? So the question is, how can we possibly protect ourselves from these kind of weapons? I even put some sort of website up there if somebody's interested in researching this in his spare time. There's no method or mechanism for defending of this kind of weapons. There's tremendous need for research in this area. Okay? Material science, heat transfer, electromagnetics, I mean, everybody comes into play. Of course, we can talk about electromagnetic shielding, lightning shielding, and so on. But this, whatever this is protecting, is going to create also induced fields in whatever it is protecting. And this is going to completely mess up all the communication with this object or vehicle and so on. Okay? Let's talk about materials. I'm glad to have some distinguished colleagues here from material science as well. This is a serious issue. Tremendous amount of money is right now spent in the US trying to take care of the fact that China produces 60% of gallium, 68% of all the production in the world of germanium, okay? Indium, 56%. My gosh, look at this. Uranium, okay? I mean, all of these important strategic elements you can find in China, but very rarely in the rest of the world. Plus also these, okay? And of course, in a few other countries, you can specifically find, for example, cobalt. Half of the world production is in Congo. Just in case somebody worries, why are there so many military coups and turmoils and whatever, Congo, okay? Anyway, platinum, for example, in South Africa, etc. Okay? Why is this so? Well, here is a list of most important rare earth elements that are extremely important for very high-strength magnetic alloys, okay? Which are of crucial importance for designing new electric car motors, wind turbine electric generators, whatever dealing with clean energy. Okay? So these super strength magnets, look at this. This is sort of maximum strength magnet obtained 1920s. Good old steel magnet, okay? But look at nowadays magnets with the rare earth materials. We're talking about of the level of 50 compared to maybe whatever, 2. So we're talking about 25 times increased maximum strength of magnetic field to be achieved with these alloys that involve rare earths. However, these rare earths, you can see here, supply risk grows in this direction, and here is importance to clean energy. Okay? So obviously, this area here is the elements which are the most crucial strategic elements. So one has to look at the possibility of designing new kind of magnetic alloys that do not have these elements. Okay? This is one of the projects I'm currently working on. Brazil is blessed with many things. One of them is it has niobium. 92% of all the world production niobium. This is remarkable. So you should all get in the business of designing and building Gatling guns, right? Because niobium is perfect material for minimum wear. So when shooting 125 millimeter grenades per second to each barrel of the Gatling gun, this barrel lasts maybe 2 seconds altogether, and it has to be replaced. But if it is coated inside with niobium, it can last 2 to 3 times longer. Okay? Well, Brazil has it. Chile has rhenium, extremely important element for very high temperature alloys. This is an example of the power of algorithms that we engineers have already created and used in other fields to design new alloys. This is example where 120 steel alloys have been created, manufactured. Their tensile stress is plotted here, and the time until rupture is plotted here, measured at 975 degrees centigrade. Feeding this 120 alloy information, experimentally obtained, into the optimization software. Optimization software created 20 new suggestions for 20 new alloys that should be better than any of the 120. Well, after they were manufactured and tested, it looks like some of them are the same quality, but a bunch of them were truly better. Okay? Higher tensile stress and higher time until rupture. This was repeated 3 more times in the batches of 20, and you can see how we were getting out of the original pool of alloys. Each time 20 new alloys, and we're getting, with the help of the optimization algorithm, getting into new territory, okay, with much better physical properties, multiple physical properties. So obviously this is something that is possible. One area which is extremely yes, I'm going to finish very soon, extremely speculative is, I'll just tell you a brief story. A good friend told me that he works in one government laboratory. He said, when I stepped out of my office the other day, I saw the guys down the hall radio controlling a moth. Moth is a large butterfly that flies at night. Okay? The moth was flying, live, real moth, was flying down the hall, and these guys were radio controlling this animal flying down the hall. How is this possible? Well, I said, when it was still a larva, before it develops into a butterfly, they implanted the microchip into a larva. Okay? So why would they do this in government research lab? Of course, Department of Defense research lab. Obviously, they wanted to control this animal, tell this animal where to fly and what to do, right? Well, if they can do it with the animal, they can do it with humans, right? So wireless sensing of human brain activity can be already measured quite well. And if we can measure something, we can surely control it. So I'm going to leave it to your imagination how we all can be zombies in the near future with somebody who can read our mind and tell us what to think and tell us what to do. Okay? So we can also modify weather according to this, and this is a sketch of one Russian scientist who was heading research center before the dissolution of the Soviet Union, which had 300 scientists. And the concept is incredible. If this is the ground level, this is about 6 kilometer level, and this is about 15 kilometer level. The difference in electric potential between top of the clouds and the bottom of the clouds is of the order of 1 billion volts. Okay? So according to the official weather scientists around the world, the amount of water which is in one huge hurricane 500 miles diameter hurricane equals to the amount of water that comes out of Colorado River in one whole year. We're talking about lots of water, right? So the official excuse is, well, so what's holding this water in the air, in these clouds? Why doesn't it fall down? Well, there's a constant updraft. It's pretty idiotic scientific explanation of something. Like there's constant vertical wind blowing, keeping this water from falling on the earth. Okay? Of course, somebody say, yeah, good Lord is doing this. I think good Lord has other things to worry about rather than holding all this water in the air. It is electrostatic force. If you can short this circuit, if you can create electric discharges here, so there's no potential difference, this water is going to come down to earth very nicely. Just think about storm. Storm comes into town, it's raining, and then there's lightning. And if the lightning hits somewhere close to your house, yes, you can hear it. But just think about it. Just a few seconds later, whoosh, you'll hear rain falling down much, much more intensely than before. This is this concept. So in other words, if we can model the three-dimensional turbulent flow with electric and magnetic, Earth's magnetic field comes into this play very nicely, we can predict at which moment and from which places inside this entire mass should we cause the electric discharges. The electric discharges could be caused by a number of means. Either you can launch missiles up to a lower cloud level, or we can shoot laser beams from above. Okay? There are a number of different ways how to cause these discharges. And the first estimate was about 60 such pinpointy discharges can basically cause the entire huge hurricane kind of type of constellation to self-destruct. Okay? Basically pour the water down and all the swirling is stopping. So if this is done already off the shore, when it is still above the ocean, then obviously all the damage to the shore is prevented. On the other hand, military got very interested in this concept, and of course you can understand, military is very much interested in creating the acts of God, okay? Which means, oh my gosh, so this happened over there, over this poor country, this huge storm and the flood and just damage them and so on, okay? Anyway, so artificial earthquakes, tsunamis, lightning, yeah, they might be acts of God, but not necessarily anymore, right? There are a number of research publications on inverse determination of the locations and sources of tsunamis and earthquakes. Why would anybody be interested in this? And they're coming from Russia, USA, and China. If we can go backwards from some measured existing tsunami or earthquake and figure out where it was the source that caused this, then we can think of how to create it. Okay? Of course, new research initiatives are also starting rapidly on understanding, modeling mathematically, simulating numerically, and of course, controlling lightning. So, enabling technologies, clearly nanotechnology, across the board, massive use of robotics and micro-robotics, so-called additive manufacturing, industry is really behind it. Huge databases use, cloud computing, not deterministic, but stochastic algorithms, and chemical computing. I have separate slides for each of them, but I'm out of steam. So I think I'm going to quit here. I'm going to thank you very much, and I'm going to ask Professor Olander to post this somewhere, Dropbox. So if anybody's interested in this, you can download the whole thing and see the rest of the slides. Thank you very much.
Thank you very much, Professor Dulikravich, for such a very nice and interesting and very broad thinking talk. Thank you very much. We have time for questions.
Walter Mannheimer, Department of Metallurgy and Material Science. Thank you very much, Professor Dulikravich, for a stimulating and exciting review.
Thank you.
I'd like to make a comment which eventually comes down to a suggestion. The suggestion, let me put it first before. You're going to stay for some time here. What I would really be interested is having this extremely interesting talk rephrased for Brazil. I find that many things, just let me give an example. I mean, the whole agricultural scenario, less than 2% of the arable area of Brazil would easily be able to take care of all liquid fuels in Brazil. I mean, the numbers are completely different, hydroelectric, everything is different. So the point why I'd like to do this comes back to your first slide of research and how Brazil performs in research, which is a morbid, I use the term expressly, a morbid issue right now in Brazil. I mean, the whole age issue, the whole citation business. For a country in Brazil, we are drowning research of interest of Brazil and maximizing research which does not necessarily benefit Brazil. The results of research are always twofolds. You must have the knowledge and you must have the market domination to yield. It is futile for a country to invest in research which is popular but on which it has no chance of developing the results. And a lot of things which I saw in your talk, you know, lead me to the idea that I think this whole idea, I mean, your idea of predicting is an extremely interesting tree on which to put another bunch of leaves. And I would like, you know, to if you could give it some thought, I mean, while you're here and talking to people in Brazil, to see whether some of the things that Brazil is being criticized for not having enough research, not to embark necessarily on research which is popular, but where the market control is totally outside of the country. Thank you.
Thank you, sir. I really appreciate your comment. I carefully didn't put the word Brazil in my title. I was trying to be general. I made some comments through a lecture here and there where I thought it might have some relevance to Brazil, but I very much appreciate your comment. You're absolutely right. Some of these conclusions actually do not apply to Brazil at the current time at all, some of them not at all in general. I also absolutely agree with your comment that it is not what we individuals consider to be important. It is what the society we live in considers to be important. So societal needs are becoming predominant, even in the US. Scientists have to much more come out of the ivory tower and do things which are benefiting average person, quality of life, and the society as a whole. So what is marketable? Yes, we all like to do certain things that we somehow like to do. But this freedom of doing things we like to do and be paid for it is sort of starting to slip away. We will have to refocus and start working on projects where there is money, where public demands things to be done. And hopefully in these areas contribute more. So absolutely agree with you. Yes, thank you.
Good afternoon. My name is Pedro. I'm a graduate student at the Department of Mechanical Engineering here. And at the beginning of your presentation, you talked a lot about R&D investments. And as a Brazilian, I know that huge investments, are not necessarily good investments. So in your opinion, could you give you 3 or 2 points, some key points on how to make R&D investments efficient?
The first and basic investment that I would suggest to Brazil is to invest in education before anything else. I think it's a basis for everything. So some of my slides, which I didn't have time to show at the end of the presentation, are addressing exactly this issue. I'm suggesting that it should start with the elementary school. There should be a massive introduction of computers in elementary school. he should move to high school. Students in high school should be provided already with the ability to program, to learn computer programming, and to use already some of the canned software. Students that are doing their bachelor's degree at university should already be definitely included in research on a regular basis. Students doing master's degrees should not just do technical part of their master's degree, but should also have exposure to business aspects. They should learn how to market these things that they're going to learn and do, how to hopefully start their own company. PhD degrees should be much more multidisciplinary. So a person who is spending 3 to 5 years doing doctorate after master's, this person should be exposed to much wider number of areas, so he can easily in the future shift his attention from one area to another as the funding moves from one area to another in the future. And of course, internationalization. So multidisciplinarity and internationalization is extremely important for PhDs. This is sort of summarized in, I think, one of the last slides that I had. So education would be number one. With general level of education in the country rapidly increased within just one generation, it is possible to lift the entire society to a new level. Otherwise, it's going to be just a very small elite, okay? And the rest of the population will have to kind of follow behind. Okay. Thank you.
No more questions? Well, so in this case, let's thank again Professor Dulikravich for such a very nice and interesting talk this afternoon. Thank you.
Thank you.
Thank you.
Thank you.